Okay, let's talk about stars as they form. Talk about how a star turns into a red giant, the famous red giants. Talk about star clusters, and then what happens when more massive stars evolve. Okay, so the main idea here is that stars, when they form, they end up on the zero age main sequence. Zero age means the exact time when the star starts to fuse hydrogen in the core. Then it becomes age 0. It is born at that point. So it's like when you are born, you are 0, and then in 1 year you turn 1 year. Okay, so 0 age, when a star forms, when it's first born, that's when it begins fusing hydrogen on the core. And at that time, its brightness and temperature will find it on the HR diagram of luminosity versus temperature. It will be on this line on the main sequence. So when the star begins burning hydrogen, its brightness and temperature will be correlated onto this line. Okay, so that's the key here. Now the idea is the higher mass stars, like we talked about last time, they form sooner and die sooner. So they live quicker, faster lives. So a type O star, remember O, be a fine girl, kiss me. So the brightest stars, O, have a surface temperature of 54,000 Kelvin. This is 40 times the mass of the sun, and it only lives 1,000,000 years before it dies. A type G star like the sun, 6,000 Kelvin, it's about 1 times the mass of the sun, lives 9 billion years on the main sequence. What does that mean? It means it's stable, burning hydrogen, keeping its size and most of its properties for 9 billion years. It doesn't change much over those 9 billion years. So you can see the the OBA stars, anything type A and above, lasts pretty short lives, 500 million years or less, and they also form sooner. So that's that's a really interesting thing. Now stars below that, type F and below, are billions of years. Look at this, a class M star like Proxima Centauri, our nearest star neighbor, it will live 200 billion years because it's burning so slowly at such a slow rate. That's kind of amazing. Okay, so what happens then when a red giant, or when a main sequence star dies, after all the hydrogen the core is burned out, the core contains only helium. Okay, there will be some other stuff in there we don't really care about, but energy can no longer be generated by hydrogen fusion because all the hydrogen is gone. And in order to get helium to fuse, you need much higher temperatures. Since the central temperature is not high enough for the sun to fuse helium, there's no nuclear energy source to supply the heat to keep the star stable. So now what happens? Gravity takes over and the core begins to contract. So if you think about it, you've got a sun. This whole time there have been two forces: nuclear fusion pushing out, hydrogen turning into helium, and gravity pulling in. And those forces are balanced like a nice tug of war. Okay? Once you stop fusing hydrogen, it burns out, the outward pressure stops, and the star collapses in. When that happens, the same thing happens when the star first formed, except now the energy, as the star starts to collapse, the temperature goes up again, and then boom, you get this like an understudy waiting in the wings of a hit Broadway show for a chance at fame and glory. This hydrogen was almost but not quite hot enough to undergo fusion. Main action sustains the star. Okay, so basically as this thing runs out of the hydrogen fuel and starts to collapse, remember the core is filled with this helium, you end up with this hydrogen burning shell around the core of helium. Okay, so so during the main sequence, it's just hydrogen burning at the core, but helium starts to build up, and then when the hydrogen is exhausted, the core is compressed by gravity, heats up again, and then you get more fusion happening in this thin layer on the outer regions. But when that happens, it actually burns quicker, and so the sun actually is going to swell up at that point and become a red giant because in order to reignite the gravity will collapse it down and then burn it at a little bit higher rate. And so then the star just gets much bigger. So for example, Betelgeuse is a red giant right now. It's, you know, huge, way bigger than the sun in radius, right? The radius of the sun is 700,000 kilometers. This is 500 million kilometers in radius. So it's just huge. Core temperature of Betelgeuse is 160 million Kelvin, whereas the sun's 15 million Kelvin. It's 46,000 times brighter than the sun, right? This is just crazy. It is, Betelgeuse is only 10 million years old, whereas the sun is 4.5 billion years old. That's very young. But it's already at red giant phase because of it was initially a high mass star. Okay, so Betelgeuse is up here in the top left of constellation of Orion, and you'll be able to see that. So this is the size of Betelgeuse there. Earth, the size of Earth's orbit is only that big. The size of Jupiter's orbit is that big. So if Betelgeuse were in our solar system, Jupiter would be within it. That's pretty crazy. Okay, so there's again the zero age main sequence. Now we have a plot that looks similar to the plot we had in the last time where the protostars were making their way onto the main sequence. This is the opposite. Once a star dies, it's going to travel off the main sequence in a different way. Okay, and so this is what, as a star dies, it moves over. Remember, the red giants all kind of hang out here, and a star becomes a red giant as it dies and moves over to the right. And so this just allows us to, again, plot the evolution of a star on the HR diagram. So we can figure out if we measure a star here with this brightness and this temperature, it's not on the main sequence, we can determine whether or not it's becoming a protostar or becoming a red giant. Okay, so there's a really interesting thing about star clusters. So there's globular clusters and open clusters, and there's two different types of them. Globular clusters only contain old stars. Open clusters contain young stars, and this is because globular clusters exist. If this is our galaxy, they are way out in the halo, and so there's no gas and dust for them to form new stars, whereas open clusters are within the galaxy, the disk, and they're still forming stars today. Okay, so here's some beautiful globular clusters. I mean, look at these things. Just so many stars. And notice the gold color. There's no blue stars in here. Yeah, I mean, there's just so many red stars, so much whatever, and just really beautiful. Whereas open clusters, look at the difference. Open clusters have fewer stars, not as many. They're mostly blue. You've got a few red stars in here, but open clusters generally are younger, and those are just differences. So you got open clusters and globular clusters. Make sure you know the difference there. Okay, and this is really cool. Okay, so in the last, again, this is an HR diagram, and we're, adults with fancy, soon-to-be degrees here, so that means we can talk about an HR diagram without the rainbow on it, but remember, this would be Roy G. Biv, red, orange, yellow, green, indigo, blue, violet, as we go over. So this is an HR diagram, which means it's plotting brightness versus temperature, which is the same thing as brightness versus color. And remember, the high mass stars are up here, and low mass stars are down here. So what this is telling you, if you plotted stars in an open cluster, for example, on the HR diagram, and remember that protostars move onto the HR diagram, okay, as they form, and remember that high mass stars form first. So this plot, if you went to this open cluster and started measuring the brightness and the temperatures of all these stars and started putting them on the HR diagram, you might get one that looks like this, which means the high mass stars are already on the main sequence. They started fusing hydrogen, they're on the main sequence, they're doing their thing, whereas the low mass protostars, they haven't quite made it onto the main sequence yet. They're working on it. They're getting over there. So they're not on the main sequence, but they're forming. They have got something going on. So this is a really good example of how the HR diagram can tell you, when you look at an open cluster, like this one, it can tell you how old that cluster is, how long it's been organizing itself based on the HR diagram, okay? And here's another one. Look at this one. All these stars are on the main sequence, but there's no stars on the main sequence in the blue region. So that means this must be a very old one, because there's no stars no young stars still on the main sequence. So only stars that live, 9 billion years or older are sitting on this thing. So that tells you that that one must be older. Yeah, here's another open cluster, some stars forming right there out of the gas and dust. They've got their own little galaxies there. So check out this one. This is even older. There's some red giants in it and no high mass stars. Look at this. And you can see that these stars are moving off the main sequence. So there's a little bit of an elbow here, and that means these stars are heading to become red giants. So they're moving off the main sequence. So this is really cool. And again, you can tell just by looking at this image, it's golder, more gold to it, which means they're older, redder stars. Okay, and the key word here is the main sequence turnoff. Main sequence turnoff refers to that elbow. It's the point where there's no more stars on the main sequence. Okay, and so what this means, again, since red stars live longer and blue stars die sooner, there are no blue stars in this galaxy, in this cluster. But there are some red giants here. And even this, look, this is the sun and the temperature. So this is where the sun is. So that means this is at least 9 billion years old, because or right at 9 billion years old, because the sun is about to die. It's about to move off. This little bit hotter star already moved off the main sequence. It's already a red giant. So these main sequence turnoff curves allow you to determine where the turnoff happened. This is 10 million years old. This is 20 million years old. This is 2 billion years old. These are 9 billion years old. So it allows you to determine the age of a cluster by plotting them. Here's another one. This is a globular cluster. And there's your main sequence, and then whoop, there's that turnoff. All these are red giants. So there's the luminosity of the sun. So now we're on a log scale, so it looks a little bit different. There's the brightness, and that's where the sun is. So there's no stars higher mass than the sun still on the main sequence, which means those stars have already burned through their hydrogen. So here's what all the stars in this cluster, if it was just formed, they would all be on the main sequence. If, or you'd have an elbow here where the stars haven't quite made it on to the main sequence yet. After 100 million years, all these stars would be dead. They would be off up here. After 10 billion years, all these stars would be dead, and you still have only these stars, the type O and not type O, the M type and K type stars would still be on the main sequence. So that's how you can determine the ages of a star cluster, is by looking at their HR diagram for those stars. Yeah, the helium flash is a really cool thing, and that's when some stars will just whoosh, get very bright. And let's see here. Yeah, so there's the main sequence. As a star like the sun becomes a red giant, there's going to be this helium flash and this little jog before it fully goes into the red giant, and then it will go kind of like woo, and then end up back down here as a white dwarf. So this is what's happening in a low mass star like the sun. You will have a helium core. You will have some fusion of helium at the center. So the sun will fuse hydrogen to helium, and then when that collapses, the pressure will increase enough to start fusing helium. When helium fuses, it ends up creating a carbon core. Just the same process. So you go hydrogen to helium and then helium to carbon. Okay, and then at that point, the star will die, and then it becomes a red giant. So you got your main sequence, becomes a red giant, the helium fusion begins, becomes a red giant again. And so, for example, the sun, when it becomes a red giant, will swell to 165 times its size. It will get 2,300 times brighter. and then it'll shrink back down to about 10 times its size, and then at that point helium will start to fuse, and then it will spread back out again from that energy to be 180 times bigger than the sun. And when that happens, towards the end, it ejects its outermost layers and it forms what's called a planetary nebula. And here's some really beautiful planetary nebula. And then after it does this, at the center of the planetary nebula is the star that created it. And that star is a white dwarf. So a white dwarf, a carbon core, just a carbon shell of a star is left over, and the outer layers form these beautiful planetary nebulas, ejecting their fusion byproducts out into space, and those are called planetary nebula. Okay, they have nothing to do with planets. They are just round and spherical, so that's why they call them planetary, but it has nothing to do with that planet at all. Okay, so anyway, all that gas and dust goes back out into space, becomes taken up into other stars and other solar systems. Okay, now that's what happens to something like the sun. It becomes a white dwarf. A high mass star, let's see, here we go. So a high mass star can fuse all the way to iron, okay, and so that means it builds up layers of an onion. It'll go through huge fusion. It'll build up a carbon core, but the carbon, there'll be enough, since the star is more massive, it'll have enough mass to actually start fusing carbon, and then it will fuse magnesium, neon, even oxygen. It will fuse silicon. The time it takes for it to fuse all of the silicon is about a day, so about 24 hours. It will fuse all the silicon in the star into iron. And when that happens, when iron builds up in the center of the star, it collapses because iron fusion will begin, but iron fusion actually takes energy rather than releasing energy. And at that point, there is no matter what happens, the star will not, even as it shrinks and heats up, it will not actually release any more energy from fusion, so it will continue to collapse and collapse and collapse until boom, it explodes, is a supernova. Okay, and we'll talk about that in the death of stars. So the main key, though, is that there's a difference between low mass stars and high mass stars in their ages and how they evolve. A low mass star will end up as a white dwarf. A high mass star is going to end up in a bunch of different ways that we'll talk about. But one of the things that we're going to talk about here is the different generations of stars. They have different materials in their cores, and we can tell whether or not a star, or throughout their composition, we can tell whether or not one of their stars, whether they lived in the place of another star or they got material recycled to them from other stars. Okay, so your main thing is to learn about how a star like the sun can turn into a red giant after it burns through its hydrogen, and then that process where it could begin fusing helium, and then how star clusters, we can use HR diagrams to figure out their ages. There's two types, the globular clusters and the open clusters. And then again, we can use these main sequence turnoff curves to figure out the ages of a cluster. A low mass star like the sun will emit a planetary nebula at its end and then deposit a white dwarf somewhere into space. And a more massive star, greater than about 8 times the mass of the sun, can fuse all the way up to iron. And then at that point, iron fusion will break down and the star will collapse. And we'll talk about that, what happens then, later. Okay, bye.